Welcome to Let's Talk About Sets, baby. Visualize yourself in your kitchen. Can you pinpoint where you keep all your utensils? What about where you place all your dishes? Are the cooking materials, such as pots and pans, kept in a heap by themselves? But what about the ingredients? In most of our kitchens, we can notice that we group things based on what they have in common. In other words, we divide them into sets, and are very clear about which material is an element of which set. Spoons are kept with a set of utensils, plates with a set of dishes, pots with a set of other cookware, and the Maggi magic syrup far away in the set of seasonings. But what are sets in the first place? Are they just groups of things that have something in common, or is there more to them? Sets are a well-defined collection of objects usually defined using uppercase letters such as A, B, or C. An element or an object that belongs to, say, set A would be denoted through writing by this, while an element that does not belong to set A would be denoted as this. To describe a set and its elements, one can use the enumeration or roster method. For example, if we have a set of vowels denoted as set V, we would enumerate the elements as A, E, I, O, and U. Meanwhile, a set of natural even numbers, denoted as set E, would have the elements 2, 4, 6, 8, and so forth. So what then would not be considered a set? Collections of objects that have an ambiguous membership aren't regarded as sets. Such examples of these are sets with elements that are beautiful. This is considered an ambiguous membership because the definition of the term beautiful varies from person to person. It's the same reason that a set described as consisting of elements that are large numbers is also an ambiguous term. One person may consider the number 10 to be a large number, while another person can consider it to be too small of a number. Sets can be either finite or infinite. Sets also have what we call a cardinality. Our previous set V, a set containing all vowels, would have a cardinality of 5 since it has 5 elements. Set E, however, would have a cardinality of infinity since it is an infinite set containing all natural even numbers. But what happens when a set contains all elements that it could possibly contain? This is what we call a universal set, denoted as U. On the other hand, a set could also contain no elements at all and would be denoted as null.
To better understand sets, we can visualize them using a Venn diagram. A Venn diagram is used to illustrate relationships between two or more sets. Consider the following example. Here, we can see a universal set containing the numbers 1 to 9. Then, we have sets A and B, which are contained in the universal set. Under set A are the elements 2, 4, 6, and 8, and under set B, 3, 6, and 9. Sounds like a lot, right? This is where Venn diagrams come in. They make sets easier to digest. Going back to our example, if we insert them into a Venn diagram, it would look like this. Our universal set would be now represented by everything inside the rectangle, while sets A and B are represented by the overlapping circles. Aside from making sets easier to understand, Venn diagrams also help make performing operations on sets easier. But before that, what are set operations that we can perform? First, we have the union of A and B. A union is a set containing all of the elements of set A and set B. Then, we have the intersection of A and B, which is the set of all elements found in both A and B. Our next operation is the set difference. This is the set of all elements of set A that are not elements of set B and vice versa. Our fourth operation is the complement of A and B. This is the set of all elements in the universal set that is not in set A or set B, respectively. Lastly, we have the Cartesian product of A and B, which is the set of all ordered pairs from sets A and B. Let's have a quick review on cardinality. It refers to the number of elements within a set. Sometimes, simply counting the elements is enough to know the set's cardinality. However, for cases where the previously discussed operations have been applied, the following formulas can be helpful. Now, if you want to find out the cardinality of the unions of set A and B, you just have to get the sum of the cardinality of set A and set B, then subtract the cardinality of their intersection. Applying this to our example, we will get the following. To get the cardinality of complement of A, we simply subtract cardinality of A from the cardinality of the universal set. If you want to get the cardinality of the set difference, on the other hand, you just have to subtract the intersection of A and B from the cardinality of set A. And lastly, to get the cardinality of the Cartesian product of A and B, we'll simply multiply the cardinalities of set A and set B.
Now we'll move on to relation on sets and their properties. In this case, we'll let A and B be sets of a universal set U. The first relation on sets we'll discuss is equality. This relation states that A and B are equal if they have exactly the same elements. Otherwise, we represent it as A is not equal to B. Next, we have the subset. Under this relation, A is a subset of B if every element of A is contained in B. If this is the case and there is at least one element in B that is not in A, then we say that A is a proper subset of B. Lastly, we have equivalence, which states that A is equivalent to B if A and B have the same cardinality. It is important to note that if A is equal to B, then A is also equivalent to B. This relation on sets then satisfy the properties of reflexivity, symmetry, and transitivity. Reflexivity states that for any given set A is equal to A and A is equivalent to A. Symmetry states that for any given sets A and B, if A is equal to B, then B is equal to A, and if A is equivalent to B, then B is equivalent to A. And finally, transitivity states that for any given sets A, B, and C, if A is equal to B and B is equal to C, then A is equal to C. And if A is equivalent to B and B is equivalent to C, then A is equivalent to C. A common application of sets can be seen in problem solving using Venn diagrams. Here is an example. Suppose that there was a gas leak at a factory. During an investigation, the authorities identified that out of 200 employees, 135 were exposed to chemical X, 85 to chemical Y, and 40 to both chemicals. But they still need to find out the following. So how do we solve these? Let's start by drawing our sets, the universal set and two more sets for chemicals X and Y. Now we know that there are 40 people who were exposed to both chemicals. Let's go ahead and put it as... For the first item, we need to figure out how many people were exposed to chemical X only. Referring back to our information, we know that there are 135 people exposed to chemical X. Before we put this into the diagram, let's remember that there are already 40 people exposed to chemical X due to the intersection of the two sets. Now we can subtract 40 from 135, leaving us with 95 people. Following the same procedure, we can answer the second item. There are 85 people exposed to chemical Y and 40 people also exposed to the same chemical. So to get the number of people exposed to chemical Y alone, we must subtract 40 from the 85, which gives us 45. We now know how many people were exposed to chemicals X, Y, and both X and Y. We can add them together to get the number of people exposed to either of the chemicals. 95 plus 40 plus 45 is equal to 180. Finally, we can subtract 180 from the total of 200 to know the number of people exposed to neither chemicals. That leaves us with 20 people.
Cardinalities of infinite sets. We say that two sets are in one-to-one correspondence if every element of A corresponds to exactly one element of B and vice versa. Consider this example. As you can see, the number of elements in set A are equivalent to the number of elements in set B. We can think of it as a perfect pairing between the sets. Everyone has a partner and no one is left out. In this example, set A and B are in one-to-one correspondence with each other regardless of which set B elements set A is associated with and vice versa. This also applies to bijective functions, where there is exactly one x in A for every y in B such that f of x is equal to y. For example, the function f of x is equal to x squared from the set of positive real numbers to positive real numbers is bijective. However, the same function from the set of all real numbers cannot be bijective because it does not have one-to-one correspondence. We can have f of 2 is equal to 4, but also f of negative 2 is equal to 4. The cardinality of the set of natural numbers. Going back to the definition of cardinality, it is used to represent the number of elements in a set. On the other hand, a cardinal number is a symbol assigned to a set to indicate its cardinality. But how do we measure a set's cardinality if there are an infinite number of elements? Consider this example. Here, we have an infinite set where enumerating each element is just impossible. However, we can still represent cardinality with Aleph null, the smallest infinite number. Sets with Aleph null are said to be countably infinite, which is the lowest level of infinity. Now consider the even and odd subsets of n. Both these subsets are infinite subsets contained within the set of all natural numbers. Does this mean then that the set of all natural numbers is bigger than that of either set of odd or even natural numbers? The answer is no. This property of the set theory is only applicable to finite sets. One unique feature of infinite sets like n, O, and E is that they can be in one-to-one correspondence or are equivalent to their proper subsets. Additionally, if there exists a bijection, we can say that two sets have the same cardinality. Let's take a look at this. In this example, we can clearly see that every element of N still corresponds to exactly one element of O and vice versa. Hence, we can say that a set is infinite if it is equivalent to a proper subset of itself. Additionally, any set that can be put in one-to-one correspondence with a set of natural numbers also has a cardinality of Aleph null. With that being said, do you think N, or the set of all natural numbers, has the same cardinality as Z, or the set of all integers? There appears to be quote-unquote more of them, as there is a positive and negative equivalent for every natural number. But can a bijection or one-to-one correspondence exist between N and Z? We can also do the same for the set of all positive rational numbers, or Q+. By moving diagonally across this table, we can ensure that every element of N is paired with exactly one element from the set of positive rational numbers. The previous examples also show some additive properties of the Aleph null, namely, the given sets N, O, E, Z, and Q+, all have the same cardinality of Aleph null.
The cardinality of the set of real numbers. Ever heard of the quote, "Some infinities are bigger than other infinities"? If you have, then you'll probably be delighted to know that this statement is in fact true and can be backed by the cardinality of the set of real numbers. The set of real numbers is also infinite, but it deals with the higher order of infinity, uncountable infinity. Irrational numbers are now added into the mix as well. Unlike sets with the cardinality of Aleph null, there is no structured way we can possibly account for all possible elements of set R. All we can do is list them randomly. We use the infinite number line or the infinite interval to represent the set of real numbers. Each point on this line represents one real number and vice versa. So how many points are there in the continuous real number line? How many real numbers are there? George Cantor, creator of the set theory, gives us a simple answer using the diagonal argument. The example above illustrates how we can always come up with an entirely new number with a different 10th digit from the first numbers, a 100th digit from the second numbers, a 1000th digit from the third numbers, and so on, given any random list of real numbers. Hence, the cardinality of the set of real numbers must be greater than Aleph null. It is uncountably infinite. For an idea of how big the number line containing the set of all real numbers really is, let us look at the binary system. When using n digits, we can uniquely describe 2 raised to n numbers. Following this logic, we can then say that if there are Aleph null possible digits, then we can uniquely describe 2 raised to Aleph null real numbers. Hence, the infinite number line is composed of 2 raised to Aleph null points.
However, infinite sets are capable of having a counterintuitive property, illustrated by David Hilbert in his infinite hotel paradox, which contains a few different situations. For all of these situations, you would have to imagine that you are the manager for a hotel with an infinite amount of rooms that can accommodate an infinite amount of guests. For the first situation, all the rooms are occupied, yet 5 people want to check in. The answer is simple. You would simply ask guests to move to the room with the number that they would get if they added the number 5 to their current room number. So the guest in room 1 would move to room 6, and so on. That way, rooms 1 to 5 would be freed up, and the same strategy could be applied for any finite number of guests. But what if a bus filled with an infinite number of people wants to check in, but all the rooms are occupied? While the same strategy used in the previous situation cannot be reused, you could ask the guests to move to the rooms with numbers that are the equivalent of their current room number multiplied by 2, or 2n. That way, the bus full of people would be able to occupy the n rooms. But what if there is not just one bus, but an infinite number of buses filled with an infinite number of people? While the solution may be a bit more complicated, it is still doable. As the hotel manager, you would create a table with the bus numbers on the leftmost column and the hotel rooms on the uppermost row. By moving diagonally across the table, you will be able to assign each person on the bus to one room in the hotel, and everyone would be accommodated successfully, since an infinite line can be created from an infinite by infinite grid. Yet what if the situation was once again different? What if all the rooms are occupied and another infinite bus pulls up with a catch? There are no seats, and the people on it are simply identified by a unique, non-terminating combination of A's and B's. So guest 1 is AABABABABAB, guest 2 is BABABBABBAB, and so on, accounting for every possible infinite sequence of those two letters. How would you be able to accommodate these potential guests? The answer is that we cannot accommodate them anymore. The strategy used in the previous situation cannot be utilized since there are no bus seats to cross the infinite amount of rooms by, and the guests will always be left out and not included in the grid. While we can accommodate an infinite number of guests and create an infinite number of rooms for them, there will still be people left no matter what. Some infinities are simply bigger than other infinities. Our entire universe is made up of sets, infinite and finite. We can definitely say that the knowledge of how sets operate can help us in our day-to-day lives. whether that involves solving survey problems to help identify employees exposed to a dangerous chemical, or managing a hotel with an infinite number of rooms to accommodate an infinite number of guests. The possibilities of encountering sets in our day-to-day lives are infinite.